The top 500 list grew out of something called the LINPACK benchmark. And the LINPACK benchmark was something that I had started back in 1978, so it even has a longer history. The LINPACK benchmark basically was a way to help us understand the performance of some software we were designing. So 20 years, it's quite impressive. I'm shocked at the fact that it's going on this long. But things have changed considerably in the intervening time, so that today we need a much broader set of metrics, much broader set of benchmarks to really evaluate a computer. We really need a whole collection of characterizations of a supercomputer to help us in evaluating what that computer is good for and how it can help us in solving our problem. I often tell people that in order to evaluate a system, you really need to run your application on the machine to see how well it works for your application.
Obviously. So Bull appeared in the top 500 list 5 years ago, and now it's regularly in the top 10. So how do you see from United States the appearance of these new players?
Oh yeah, so I would say that competition is good, so it helps motivate everyone along the line. From the standpoint of the European community, Bull certainly is a very strong player. Japan is a very strong player in high-performance computing. China is now aggressively pursuing deploying high-performance computing. Bull certainly has a strong presence here in France and in Europe.
Exascale will be reached in 2018 and 2020. So what new kinds of application we will solve thanks to the computer that will have this huge size?
Right. So these big machines are used to really help us advance science, and they should be thought of as very specialized tools or instruments that help us in understanding science. Really, they act as crystal balls. They act as ways to help us predict how things will work in the future, how things will behave in the future. The first way they help us is they provide much quicker time to solution. They're faster machines, they provide quicker time to solution. And the other way they help us, the other dimension that we gain an advantage, is in that we can solve bigger problems, and we can have more fidelity, more accuracy in our solution. So as we grow, as our machines grow, we're able to solve problems faster, and we're able to solve them more accurately, so we get a better picture of what's happening. And it'll help in terms of predicting the weather. It's helping us in terms of understanding what the climate will be in the future. It helps us in terms of designing better combustion engines. It helps us in terms of developing nuclear power. It helps us in terms of building better materials, perhaps. Life science applications clearly have applications in this way. It helps us in developing better fuels. They help us in ways which we couldn't do through theory, that we couldn't do through experimentation, physical experimentation. They allow us to simulate the future, basically.
Nevertheless, reaching this exaflop or this exascale machine will be somehow very hard. What for you is the next hurdle we will have to go through?
Yeah, so there are many challenges as we move towards exascale. Today, if I just take today as an example, our fastest computer has 1.5 million processors in it, 1.5 million processors. And for exascale, we will need to make computers which the current thinking is on the order of 1 billion threads of execution, 1 billion threads of execution. That number seems so distant and so unbelievable today, but we will reach it. And so one thing is trying to effectively use 1 billion threads of execution, have a programmer choreograph and orchestrate all of those processes in solving a problem. So that's one challenge, I think a very serious challenge. Other challenges that we face relate to things like power consumption. So these machines are very power intensive. They require a lot of power to run the machines. Our fastest machines today take approximately 10 megawatts. 10 megawatts of power are required to power those computers. In the US, I think of 1 megawatt as being the equivalent, if I run 1 megawatt for 1 year, it costs $1 million.
Yes,
So in France, perhaps it's the same. And think of just turning the computer on today would cost $10 million just to turn it on. And today, the current thinking is the Exascale computer should be limited to 20 megawatts. And to design a machine at that power envelope is very challenging for the.
To divide by 10 the power consumption.
That's right. And we have to increase the computing power by three orders of magnitude to get to exascale. The other challenge, and perhaps is the most serious challenge, these machines are not cheap. And these machines need an investment in terms of research that's needed to get us to that point. We can't wait to 2018 to start thinking about that. That has to be done today. So it requires research effort, it requires government investment in terms of not only the hardware aspects, but the software aspects.